Conjugate pairs differ by 1 H+. A Bronsted-Lowry acid gives a H+ or a proton, and a Bronsted-Lowry base accepts an H+ or a proton. When acids and bases are conjugate pairs, their Kas and Kbs are also conjugate pairs. So if we have a weak acid, HCN, it dissociates into H+ plus Cn minus. HCN is an acid, so it has a Ka of 4.9 times 10 to the negative 10th, while its Kb is 2 times 10 to the negative 5th. These values tell you that HCN is very weak acid, therefore their conjugate base is much stronger. In the next example, NH3 ammonia is a weak base. We reacted with water. The conjugate pair for ammonia is NH4+. Based on the numbers here, Kb is much stronger, so NH3 is a stronger base, therefore its conjugate pair is a weaker acid. Since Ka and Kb are conjugate pairs, when we multiply Ka and its Kb, it will equal to Kw, 1 times 10 to the negative 14th at room temperature. If we look at the previous problems up here, if I multiply 4.9 times 10 to the negative 10th times 2 times 10 to the negative 5th, it will equal approximately 1 times 10 to the negative 14. Same goes for ammonia and ammonium. 1.8 times 10 to the negative 5th times 5.8 times 10 to the negative 10th is approximately 1 times 10 to the negative 14th. So if we take the negative log of each Ka, Kb, and Kw, the equation becomes negative log Ka plus negative log Kb equals to negative log Kw. Remember, when we multiply logs, we are actually adding logs together. So right here is actually a plus, but we're doing a minus log. We stated in the previous sections that negative log is the same thing as P. So we could rewrite this formula as pKa plus pKb will equal to pKw. So in essence, as we stated earlier, a stronger acid will have a greater Ka, therefore its conjugate base, Kb, is smaller. So a stronger base with a greater Kb is conjugate acid, Ka will be smaller. They're always opposite, but if we multiply Ka and Kb of the conjugate pair, it will always equal to Kw at a given temperature. At room temperature is 1 times 10 to the negative 14th. Polyprotic acid is an acid with more than one H+ to dissociate, so it has more than one hydrogen ion that it could give away. There are 3 types in general. A monoprotic is one that is able to lose one proton or one H+ ion. Remember, a proton and an H+ and H3O+, the hydronium ion, all mean the same. Examples of that is hydrochloric acid. If I break that apart, since it's a strong acid, it will dissociate into H+ plus Cl minus. Hydrocyanic acid is a weak acid. It would dissociate into H+ plus Cn minus. Both of these examples only contain one hydrogen. Note that strong acids has one arrow because it completely dissociates. Weak acids and bases will have double-headed arrow because it will establish equilibrium because it only partially dissociates. Diprotic. Di means 2, is able to lose 2 protons or 2 hydrogen ions. Example of that is carbonic acid, which dissociates into H+ plus HCO3 minus. The hydrogen carbonate ion can further dissociate into H+ plus CO3 2 minus. So carbonic acid has 2 hydrogens. Individually, it will release 1 hydrogen ion at a time. Triprotic, tri means 3, is able to lose 3 protons or H+ ions. Example of that is phosphoric acid. H3PO4 dissociates into H+ plus H2PO4 minus. H2PO4 minus can now dissociate to H plus HPO4 2 minus. HPO4 2 minus would dissociate into H plus PO4 3 minus. So this one has the ability to give off 3 H plus ions. Since polyprotic acid is able to give off more than one hydrogen ion, it will have more than one Ka, or equilibrium constant, for that acid. In general, if the respective Kas are 1,000 or 10 to the third or more, the concentration of H plus and its pH will only depend on the first hydrogen ion dissociation, because the following Kas are so small it barely dissociates anything. The reason so is, as you remove more and more hydrogen ions, it becomes more difficult to remove the next H plus ion, because the molecule that was positive becomes more negative in charge. Example, H2S, hydrosulfuric acid, dissociates into H plus HS minus. It's Ka1, which is the dissociation of the first hydrogen, is 1.0 times 10 to the negative 7th. We take the HS minus ion and dissociate it again, and H plus to S2 minus. Our Ka for 2 is equal to 1 times 10 to the negative 19. So the difference between negative 7 and negative 19 is so big, the second dissociation will hardly contribute to the H plus ion concentration. So we could just look at the first dissociation. Phosphoric acid is able to ionize 3 hydrogen ions. Its first Ka is 7.1 times 10 to the negative 3. Its second Ka is 6.3 times 10 to the negative 8. Ka3 is 4.2 times 10 to the negative 13. These are much greater than 1,000. It will only depend on the first reaction. So even if you calculate the equilibrium table for the Ka2 and Ka3, it will make very little difference. So in general, Ka1 is always greater than Ka2, which is always greater than Ka3. Conjugate bases are also called polyprotic bases. For example, in the above problem, we notice the phosphate ion can actually take in 3 hydrogen ions to become phosphoric acid. And then S2 minus is a diprotic base because it could take in 2 hydrogen ions to become hydrosulfuric acid. Neutralization reaction is an acid plus a base that yields a salt and water. A salt is an ionic compound in which the cation is from the base and the anion is from the acid. So this is an ionic compound. The reverse reaction of a neutralization reaction is called hydrolysis of a salt. So what we do is we just reverse the reaction. We take the salt, react it with water, and it will yield acid plus base. Both of these reactions are double replacement. So you see the cation will replace the cation and they'll swap partners. There are 4 types of salts. A strong acid plus a strong base will yield a neutral salt and water. If I look at my salt, the cation is from the base and then the anion is from the acid. Since it's a strong and a strong, they cancel each other out. If I take a strong acid plus a weak base, it will yield an acidic salt and water. Perchloric acid is a strong acid. Magnesium hydroxide is weak. The cation is still from the weak base. The anion is from the strong acid. Since the acid is stronger, the salt becomes acidic. A weak acid and a strong base will yield a basic salt and water. The cation is still from the strong base. The anion is from the acid. Since the base is stronger, the salt is basic. A weak acid and a weak base will produce an unknown salt and water. pH of the salt is dependent on the Ka and the Kb of the weak acid and weak base. If Ka is greater than Kb, it is an acidic salt. If Ka is less than Kb, it is a basic salt. We learned about binary acid and oxyacids when we were learning the nomenclature for an acid. A binary acid is a hydrogen plus an element. These are elements off the periodic table, so it contains no oxygen. In general, the element needs to be more electronegative than the H plus ion. This is why they're mostly on the right side of the periodic table. In general, acidity increases up the periodic table except for hydrofluoric acid, which is due to its size. The general nomenclature format is hydro plus root plus ic acid. Oxyacid is a hydrogen plus an oxygen plus elements. Oxygen is present, so in general, these are your polyatomic off your polyatomic sheet. Donated H plus is always attached to the oxygen when we draw the Lewis dot structure. Acidity is determined by the electronegativity of the central atom and the number of oxygens. If it has an 8 ending, it's a root ic acid. If it's an ite ending, it's a root us acid. Remember, there is no hydro in front of oxyacid. Oxides are compounds with at least one oxygen present. There are two types: metallic oxide, which are metals on the left side of the periodic table, and then non-metallic oxide, which are nonmetals on the right of the periodic table. Metallics are hard, insoluble in water, and they have high melting points. Non-metallic are just the opposite. They're soft, soluble in water, and they have low melting point. Both of them can be ionic or covalent bond. Metallics in general will be ionic compounds. Non-metallic will be covalent compound. The general format for metallic oxide is metallic oxide plus water will yield a metal hydroxide. The examples below is copper oxide plus water yields copper 2 hydroxide. Potassium oxide plus water will yield potassium hydroxide. Non-metal oxides plus water will always yield acids. The way you write equation is you just add them. SO3 plus water. And how do we write this? There's 2 hydrogen, there's 1 sulfur, and there's 4 oxygen, and that's how we get the sulfuric acid. In the next one, we have dinitrogen trioxide plus water, 2 hydrogen, there's 2 nitrogen, and it has 4 oxygen. And what we do is reduce, and that's how we get nitrous acid.